Okay, so chapter 10. What we're going to look at in chapter 10 is something very important to us, obviously, living in Florida, considering we're a peninsula, surrounded on three sides by ocean. I could have not thought of a better place in the United States to live, to be honest with you. I grew up in the western part of the United States, West Texas. My dad was in the Army, so I moved a little bit. Then I was living in Pacific Northwest, which is beautiful, but my goodness, the weather. But coming down here to Florida, someplace, oh yeah, beautiful. Listen, have you ever been there? Do whatever you got to do. Stow away. Everybody will say, oh, I went to Hawaii. I was kind of disappointed. No, it's more beautiful than you imagine. I've never seen water that color. The water was the color of turquoise. It was absolutely beautiful. Absolutely one of the most. And sailing around Maui was one of the most beautiful places I've ever seen in my life. So, but geez, expensive. But I don't know. Stow away on a ship or something. Was your boyfriend in the Navy? That's the only way I got to go. Oh, awesome. Oh, how nice. Look, that's like my dad was stationed in Greece for a while. That was very cool. We lived on one of the islands. Okay, so let's talk about the beaches. We've all been to them. We all love them. I know you love them probably as much as I do. So let's talk about what it is out there on the beach. So the next time we're there, we can say, oh, I recognize some of this stuff. So first thing we got to do is throw in a little bit of terminology, and this might seem kind of obvious, right? But nonetheless, let's put it in there. What's the shore? Well, the shore is the area between low and high tide. So it's the area on the land in which the waves coming up affect, right? And while that may not mean so much just as a definition, think about what that means to an ecosystem. So if you live in that shore area where you're affected by the tides and by the current and the waves and the strength of the waves, you're probably going to evolve very special adaptations. And that's why, for example, like barnacles have that really strong glue that they can hold on to stuff with. They're called byssal threads. Yeah, they got this really strong glue that they can hold on to. People are trying to recreate it because it can stick really well underwater, but that reflects kind of where they are, right? So the coast, of course, is inland from that, and we say ocean-related features. I think that probably goes everything from the dune line to the hot dog vendors, to the people selling T-shirts, probably here in Florida anyway. Along the coastline is the shore, of course, between the coast and the boundary. The back shore is above high tide. Okay, so the back shore is never going to get flooded, although it can occasionally get flooded in hurricanes, right, with storm surge. And that's a problem, of course, because organisms in the back shore typically aren't used to water, right? It's above the high tide shoreline. So whenever there's extra energy in the waves, then that becomes an issue. That area in between the tides, the one in which you probably would find most of the organisms, most organismal adaptation going on, is going to be that intertidal zone, right? What we call the littoral zone. That's the part that's underwater in high tide and exposed during low tide. So organisms there are dealing with drying out, heat from the sun for half the day, and then the other half of the day they're submerged. So if they're filter feeders, they can only feed when the water's in, and if they feed on organisms in the surf, then many times what they'd have to do is they'd have to, in the water, they have to dig down in the sand during the day when the tide's out in order to survive, right? So that's going to be a really dynamic area there. The near shore area is going to be from the low tide out to the breaker line. That's an area that's not typically ever exposed, except sometimes through tectonic events or through what we call eustatic changes to the ocean. Eustatic changes to the ocean level means changes all over the globe, but sometimes these near shore areas end up being exposed. And then way out there where the best stuff hangs out, obviously, is the offshore. I've flown over the beach several times when we were doing dolphin work, and man, I tell you, you look between the inshore and the offshore. And inshore, it's all the bathers and the folks at the beach, and the offshore, it's it's the sharks and it's the whales and it's the big stingrays and all that sort of stuff. So it's a completely different area. The beach, what we call the beach, again, is that area that we all hang out on, the recreational beach. So that's sort of a really kind of general term. The berm, and I'm going to show you some pictures of this too as we go through. The berm is that kind of, if you've ever been on the Canaveral National Seashore, you've seen the berm. I'll show you, like I said, in just a second. Usually at the coast of cliffs, like in California, there's a really well-developed berms. The beach face is that area down closest to the beach. It's really great for walking or running on when it's low tide, you know, where the sand is compacted down. It's flat as a mirror, man. You can just go skimming across there. It's where the kids really are going to like to do the boogie board thing, right? Because it's flat and you get just that little skim of water. It's great for jumping on and breaking your leg, obviously. Way offshore is this wave-cut bench, and that's caused by the waves breaking and circulating. Let me get my little pen here. Oh, a second. Sounds like Cooper's digging into something. Cooper, what are you doing? Yes, you were. Yes, Cooper was in the garbage. All right, anyway. Okay, so what was it? Oh, the wave cut bench. The waves, when they're breaking on shore and coming back, you know, the force, right? So they're causing that cut into the bench and developing that longshore trough. And then off of that is a sandbar, the longshore sandbar. Now, out at Siesta Key, out on the West Coast, my family goes there every summer. We all spend out. And these, well, let me show you the pictures. These characteristics are really obvious. Okay, so here's one of Canaveral National Seashore. There's the berm, right? The berm is usually going to be that area kind of where the weed line starts and back into, and as I said, it's up against sandy beaches here. It'd be more rocky if you were out there in California. And then there's the beach face. This is what I mean by a wave-cut bench that got elevated, sometimes through tectonic or through the water level dropping. Here's another in a wider beach. This is Siesta Key again too. There's the berm right there, and you know when you're walking to the beach, you know what I'm talking about. You walk and there's a little bit of a rise. That's going to be the beach face, and then you get into the beach. There's the breakers. This is a cool picture, isn't it? Look at that. I don't think that's Photoshop, and that's a good size animal. Did I stick that in there? I don't think so. This is Siesta Key. Look, that's what I'm talking about. The longshore trough, the dark area. Right there. So especially in low tide, you can almost walk out to the sandbar, but in high tide, you do have to swim. So you can walk across this area here. Yeah. Too sickle shaped for a dolphin. And then you walk across the shallow area and then swim through the sandbar. So, you know, when you've been to the beach, you feel these features. So the next time you're there, you'll know you're walking through the beach face, down into the longshore trough, out to the sandbar. And then, of course, I like to go, my wife was always having a fit. I always like to go this part of the sandbar because that's where the dolphins go. The dolphins move up and down that sandbar, especially in the morning, feeding on the mullet and the small fish that hang out there. And if you remember, like from our discussions of upwellings, that sandbar, you know, this is the continent side, okay? As the water hits, it comes up from the bottom, so it brings up nutrients. If you live in Florida and teach in this class, I always feel my obligation to remind everybody about riptides. This is what riptides look like. Very obvious. You can see the water's being pulled back into the ocean. There's a riptide. There's a riptide. Everybody's seen one of those, right? And we all know how to avoid those, don't we? You don't move back into the rip. That's gonna you get exhausted and you'll probably drown. You're gonna move parallel to the beach. Riptides are usually very narrow, so you can usually get around them. Right? Always amazes me. Not amazes me. I feel bad for the folks, but you know, they hear about them like just, gosh, you're literally, I don't know, how wide is that? Maybe 30 feet. I mean, you could, and sometimes, you know, it's just better. Just let yourself be carried out. You know, it might get a little bit scary, but you'll eventually get out of it. I got caught in an outgoing tide down to the Keys one time between a bridge. Whew. That was a pain. All right, where was I? Oh, riptide. All right, next thing. Okay, how does sand move along the beach? Well, two ways. It moves up onto the beach, okay, and something we call swash and backwash. It's not the same thing as someone does into your beer, though. But swash is when water rushes onto the beach and it soaks in, and backwash is when the water drains back into the ocean. Now, that the significance of that is that changes throughout the season, okay? In the summertime, when the weather is milder, the water, you know, oh, the best time to go to the beach, right? The water's just, you laying there half asleep, and the water's just, and it's soaking in, isn't it? But in the wintertime, when it's rougher, it's more of that backwash. Now, what is that going to do? We'll look down the pictures down below. It's going to change the topography of the beach, right? So in the summertime, it's going to push the sand up closer to the rock, okay, or the part that it can't move anymore. and because the long, beautiful, slow waves, here I am sitting on my mattress, or laying on my mattress, enjoying myself. And in those short high waves, you're going to create that sandbar. So what we get in Siesta Key oftentimes is because of the summer storms, we get that development of a sandbar, even though it's in the summer. Right? So you get those waves pushing in. And also because Siesta Key is also shaved. It's shaped in a crescent. So it tends to amplify the wave action a little bit. And then, of course, not only perpendicular, parallel. And parallel is called longshore currents. And parallel come because of the fact that, as we talked the other day, the waves rarely ever approach the beach head on, right? They usually approach the beach at an angle. So as they approach the beach at an angle, what it does is it makes the beach, or the sand particles, actually move in a zigzag. So they get washed on the beach, and then they get backwashed, and then when they get backwashed, the waves push them this way. So they move up the beach and down the beach, and up the beach and down the beach. It's a zigzag pattern, okay? So the net movement is along the beach in a parallel. It's called a longshore transport, or beach drift, or littoral drift. Littoral, again, is that high tide to low tide area. So this is going to be affecting that area quite well. And it can move pretty quick, 2.5 miles an hour, it says there. It's amazing the volume, though. Look at that, 300,000 cubic yards, 17,000 cubic trucks in a year. So that's a lot of sand that's being moved down the beach. Now, we'll talk a little bit later on about some of the problems that causes. In a normal environment, though, typically the sand that's being lost down the beach is being replenished from further up the beach. But that's in a typical environment. So we talk about that a little bit later, though. Okay, so we have also different types of shorelines, right? And it depends on what's happening there. Is erosion happening there? So are you getting cliffs? This is going to be in areas where you don't have a lot of time for the rock to be ground into sand. So you're not going to get it's not going to happen along those passive margins where, everything's kind of staying very calm and the shoreline is eroding into rocks and then into sand. This is in areas where there's going to be some tectonic uplift, some tectonic activity. So the continent is being raised up. So new rock is constantly being exposed to the eroding ocean, right? This is what's happening out on the Pacific. So you're going to get areas like the headlands, you're going to get areas like bays, and those two areas are going to affect or the way the waves strike the beach are going to create those two areas, which are then going to reinforce what's happening to them. Let me see if I can explain to you. When the headlands begin to form, when they're really, really small, before it's that very deep sort of curve that you see there, that little bit of excess energy, see the wave energy is being concentrated there, begins to make the headland worse or make it more of a headland. And then as that time goes on, more and more wave energy, more and more, and it gets dissipated in the bays. And again, the wider they get, the more that's reinforced. Okay, you've seen it at the beach. It's the erosion of sand. Now, if you're doing it to rock, you can create all these things like these cliffs. We don't see any of this here in Florida, unfortunately, but all these really neat caves and arches that go through. I remember when I was a kid in Greece, there was a really neat sea cave that I found that took me all summer, but I finally got the nerve to swim into it. This is what it would look like. This looks like typical sort of California coast. And if you get that tectonic activity, you can actually get the wave-cut beach to be lifted up. Is that when do I have that picture? A little bit later. I might have put that picture a little bit later. All right, so this is going to happen on the side of the ocean or along those shores in which you're going to have that constant replenishment of new rocks. So you're constantly eroding it. Now, if this shore stopped becoming moved up or becoming tectonic, well, then eventually all this stuff is going to be ground into sand. But that's not going to happen along an active margin. So that's not going to happen along the Pacific coast. Now, in those other shores where you have this it's what we call a depositional shore. Now, this is a shore that's gradually subsiding. So it's being eroded. So you get things like barrier islands, right? You get a lot of sandbars and sand deposits. You get bay barriers. You get bay mouth bars. You get spits, and spits are always really cool because the way the water rushes in the opening, it causes it to curve back. You get these really neat things called tombolos. So there's a tombolo. Now, tombolos oftentimes, the cool thing about it is only accessible during low tide. So if you're out there hanging around that rock, and sometimes it gets pretty deep in this area, if you don't make it back at low tide, it's a pretty good swim. Of course, that would be exactly where I'd go. Deltas are formed on depositional shores. So we're obviously talking about our end of the world, right? So we're talking about Florida, the Gulf of Mexico, barrier islands, right? Merritt Island, all of that out there. Those are all examples of barrier islands, right? There you go. There's some barrier islands. See? So you get the ocean. This may be one I've just almost looks down around Sebastian or Vero. Looks like one of the causeways. But you get a lagoon area inside. This is what is this? I don't remember where I grabbed these pictures, but that's obviously a barrier island. From space, you can look at the spit. That's neat. You can see it. And that's because as the water rushes in, it forms that. And then down around the Mississippi River, we get like the delta. Right? So these are depositional shores. This is where erosion has taken over the rocks, and you're not making any new rocks because it's not tectonically active. And so it's making these ridges and these sandbars and these spread out of deltas and sand, you know. So it's not, it's not constantly having to erode the rocks. So it's able to move these big chunks of sand around. The nice thing about barrier islands is for those of us that live on the mainland, they actually provide like a speed break, if you will, or a speed bump in the road. If there's high wave activity, like during hurricanes or just seasonal storms, it's the barrier islands that usually take the brunt of it. They're usually the ones that absorb the energy first. Doesn't mean that those waves can't affect and go into that lagoon area, like into our, into our Indian River Lagoon. This looks like it's down near Jupiter in that area too. Well, there we go. Let me get a different color. Blue on blue won't look so good. But there's Canaveral and there's our lagoons. So barrier islands can be, barrier upon barrier, if you will. It's like a ridge of islands. So that protects the mainland from the wave activity. Right? The barrier islands absorb it. Now, this whole creation of barrier islands that we see is all related to the end of the Ice Age about 18,000 years ago. And during the Ice Age, the warming that occurred caused water to just gently flood over. You remember the path active margins are sharper. So that's the west coast of the United States. And passive margins are more sloping. If you think about it, it's kind of a triangle. So what's been going on is, as the water level rises, relatively speaking, it doesn't seem to rise as much on that side, but here it rises quite a bit further. So you get this flooding to these inland areas. So they're all tied together to the climate, right? These are great places for people to live, great places for people to vacation. That's why the population, if you can afford it, has risen so dramatically, 14%. Who'd on the ocean? But that's a problem that we'll talk about. That causes damage to these very important barrier islands. Causes damage to these things that are supposed to protect us. There's over 2,300 of those occur along the Atlantic and the Gulf Coast, and man, they are beautiful, no doubt, right? Now let's look at them on the side and see how they work. There's the ocean side, the ocean beach. There's the dune, which if you've ever been to the beach, and I know you have, you might remember this sign that says unlawful to pick sea oats. Doesn't look very good right there. When I first moved to Florida, these are sea oats on the left. I always wondered, what the heck? I looked up online. Heck no, I didn't look up online. I asked somebody, or I found out some way that they weren't endangered. Do you know why it is unlawful to pick sea oats? I mean, I finally found out, but can you think about why there might be a reason? Well, plants hold land in place, whether it's trees holding soil or whatever. So sea oats, no, they're not invasive. Sea oats actually hold the sand dune there. And remember, we want to protect the beach. We don't want to erode the dune. Now, erosion of the dune occurs, say, during storms, and that's part of the natural cycle. But during the less storm, during the swash periods, sand is being deposited. And it's great if you have these sea oats growing because they grow roots down into the sand and they hold it in place. They stabilize the dune. Okay, so if you pick them, then you might potentially ruin the dune. And the dune is all part of the beach ecosystem. They're all tied together. Dunes are eroded, and during storms, they're built. And during storms, they're also eroded. It's this pushing back between the sand and the water, right? Yeah, exactly. The barrier flat is going to be passed, and usually the barrier flat is going to be grassy. It might get flooded during a storm surge, but we're going to start to see, this is a barrier flat. This is a Canaveral National Seashore. I recognize the trail. This trail right here, actually. But this is what I mean by the barrier flat. Could be a good place for snakes and gators for sure. And then that begins to slope down into a salt marsh, which is either low or high, depending on where the highest neap and the highest spring tides reach. The thing that's interesting about barrier islands is they actually move. There's actually a general tendency, because of the way the erosion works, for the whole column of beach barrier island to move this way. Oh, come on, pen. To move this way. It's called barrier island migration. One of the ways we know that is, see the peat bed down here? Peat is coal, right? It's decomposed organic material. Well, we noticed something interesting was happening in the peat beds in some barrier islands, is they were being exposed on one side. So we came up with this idea, or this theory of barrier island migration, and this is caused by the rising of the sea level. So it's very influenced by global climate change. And the reason why that is as the sea levels rise, there's more water that can splash over the island. But what happens is, as the ocean is pushing in, start the picture in the upper right, as the ocean is pushing in, it's eroding that part of the beach, and the island is rolling over on itself, right? As it's depositing material on the backside. So you have this water, that's pushing over the beach, and it's actually forcing that barrier island from the right to the left. Now, as I said, the peat deposits, these outcrops that occur, those let us know that this is happening, because where they started, they would have started under that back marsh area. Where all that vegetation is growing, that's where you're going to get a lot of silt being deposited. You're probably not going to get as much silt on that side. The ocean's washing it away. This is calmer water. So you're going to get that silt deposition, and then that silt's going to be packed in and more packed in, and eventually it's going to get turned into peat, which could get turned into coal, right? That's how it works. So when we started or noticed that there were peat outcrops on the front of these, we knew that this part of the island must have at one time been here. So it's been moving this way, right? Or that part of the island moved to there, not was there. So eventually, through time, what happens to barrier islands? They just kind of merge with the mainland. And then out to sea, the processes begin again to start forming more barrier islands. Unless, of course, we have the global climate change thing. We change the sea level. See, this is all tied to that. Okay, what about a delta? The biggest delta, the one we're most familiar with, is the one in the Mississippi River. This is very simple. This is water flowing out. It gets out into the ocean, it slows down, and so the sediment, the material that came down in the river, starts to deposit. It drops, right? There is a relationship between how fast water moves and then how much sediment it can carry in solution. And when water slows down, it's like if you shake up a bottle of sandy water. As the water settles down, the sand drops to the bottom. So these deltas move out, and they form these triangular shapes, and have all these little rivers in them for these depositions these things called distributaries, which are formed because of the fact that erosion is working, but you're dumping in there faster than erosion. So you're kind of backing up the system. So the water flows down, and it gets blocked. Right? Because deposition exceeds erosion. So it tries to find another way to get to the ocean, so it goes out this way. And then that area gets blocked. So then it goes out this way. And then that gets blocked. And then it goes out this way. And then it gets blocked here, and it branches off there. And then it gets blocked here, and it gets branched off there. See, so you're making that that sort of spider web arrangement. Now, in the Mississippi River, what we have is a situation in which deposition is exceeding erosion. That's why we're getting that branching. If you look at the Nile River, the delta's it's more like a fan. It's smoother. You don't see all the little rivers. And that's because the other is happening. Erosion is exceeding deposition. And that depends on what's going on upstream, obviously. Now, the thing with the Nile River Delta, the reason why it's eroding is because way upstream they built a dam many years ago, back in the 70s, I think, the Aswan Dam. It supplied electricity and changed the whole economy of Egypt. But the problem with that, it was just trapping a lot of sediment upstream. So if dams are really bad about trapping sediment. And so when it's stuff in the water trapped behind the dam. So therefore now the water that flows through the dam is less sediment, and so you're going to get less deposition. Right? You're going to get more erosion. The water is going to be more water than stuff floating in it. I went to Huma, Louisiana many years ago when I was in grad school, and Huma, Louisiana is basically not in this picture of the Mississippi River, but it's right out on the delta. And I remember standing looking down the road, and the road kind of ran right off into the Gulf of Mexico. I mean, it literally seemed like it was just inches above the Gulf of Mexico. All right, now, so these longshore currents that I was talking about, with the combination of those in the river, what you're going to get is water moving down the coast, okay? That's the parallel motion. And rivers are going to be dumping sediment material into the ocean. So you're going to get this average direction you see of the longshore transport, and that's the movement of material. All right, so the rivers supply the floating stuff. The longshore current supplies the sand, and you're going to create these beaches along this longshore current. Now, of course, it's all got to be balanced. And you remember we talked about geological structures under the water. One was a submarine canyon. So a lot of what happens is, like you see in, don't worry about it, Redondo Canyon. I used to go to Redondo Beach. Redondo Canyon and Newport Canyon, La Jolla Canyon, that's where that sand gets dumped back out. So the sand moves down the rivers. It's then moved down the beach by the longshore current, and then it flows out into the ocean through the canyons. That's all the natural process. All right. So basically what's happening is you get this movement of material down the beach. It's when human beings get involved that we impede that movement of the sand, in which we start to screw things up. So we'll get to that in just a second, but let's kind of continue on more talking about the characteristics of the shoreline. All right, two shorelines out there. There's the emerging and the submerging shoreline. And an emerging shoreline is, well, it's just what it says. It's one that's above the sea level, right? It's currently above the sea level. This on the right is an emerging shoreline. The first marine terrace, the second marine terrace, and the third marine terrace, those are those wave-cut benches I was talking about. So you're going to find those marine terraces on areas where either tectonic activity might be pushing the land up or sea levels are dropping. Okay, either one would do that, or maybe a combination of both of those. Submerging one's the other thing, right? That submerging shoreline, what you would have is you would have a shoreline below the sea level. So you have beaches that are drowned. You would have submerged dune topography. Okay, now I'm cheating here. That's not really submerged dunes. That's really the way the ripples that cause on the beach when the waves are breaking. But I couldn't kind of find a really good picture of these submerged dunes, so I just kind of used that as an example. Out in California, in Tampa and in California, those are both drowned river valleys. The one in California in San Francisco is drowned because of tectonic. The valley that is San Francisco Bay just kind of dropped and water rushed in. Whereas in Tampa, it was basically a matter of the water level rose and it kind of flooded in. But it's a drowned river valley. So, of course, this means that changing sea levels decides what is an emerging and what is a submerging shoreline, right? I said emerging and submerging can both be tectonic activities, but it's also changes in sea level. And changes in sea level can be in addition to these tectonic movements, right? Now, we've talked about tectonic movements before, but one of the things that we didn't talk about was this stuff called an isostatic adjustment. All right. Now, what I mean by an isostatic adjustment, this is just absolutely unreal for me to think about, is look at the second picture. When the glaciers formed, and I got the picture down the left to kind of show you 20,000 years ago, the part in the white was covered in glaciers, and glaciers weigh a lot. They can be up to 2 miles thick. When the glaciers form, a 2-mile thick chunk of ice weighs a boatload, right? And it pushes down on the crust. It actually causes the crust to warp, okay, to kind of squeeze out the sides where you see the uplifting. Now, later on, the ice melts. So guess what the middle part does? It rebounds. So it's kind of like pushing on a mattress, right? And coming back up. That rebound doesn't happen right away. That rebound, for example, in the area in the picture where you see the glacial sheets today, those glaciers melted, what, 10,000 or so years ago? And that area is still rebounding. It's still bouncing back up. Tectonic forces work very, very slowly. Okay, well, these areas, like where I'm pointing to the Hudson River is under, the reason why there's water in the Hudson River is because there's a depression where there was a glacier. The glacier pushed the continental crust down, and then the glacier melted. There you got the Hudson Bay, not Hudson River. Hudson Bay was the water from the melted glacier, and the land is rebounding. Now, I don't know if eventually Hudson Bay will become dry, but you think if it does level out, then it would. The water have to go somewhere. So that's going to change in sea level more like in a local area, right? Like in an area where you might find a glacier. But the eustatic changes are all over the world, okay? And they're caused by all kinds of things like inland lakes being formed as like local areas change in water. As the glaciers melt, right? As they melt, the water levels go up. And as they form, the water levels go down. Water also expands when you heat it up. They think, you know, how much could water expand when you heat it up? Well, not very much in a glass of water, but in an ocean, that would be a lot. Then, of course, there's all what we're doing with this, right? All the habitat destruction we're engaging in, all the fossil fuels, all that stuff we're doing that might be, you know, if not being the initial cause. That's what people got to understand about global climate change. We're not saying that it's just humans, but everybody agrees that humans are making it worse. We don't know exactly where the tipping point is. That's what people got to understand. Okay, so the end of, or the Pleistocene, which was the last era, ending of the last ice age, and that was 10,000 years ago. We're in the Pliocene now, or Holocene, excuse me, Holocene. So the Pleistocene was 2.6 to about 10,000 years ago. Went through several ice ages. Short ones and long ones, and the sea levels changed. They were in some point 400 feet below where they are now. And that's when there was a glacial maximum at about, what, 18,000 years ago? See, once again, that's one thing that people who don't understand global climate change argue against, is they say, well, I mean, the Earth has gone through glacial periods, warming and cooling throughout time. That's true. This is long before humans could have any effect on glaciers, and the Earth was cooling and warming. That's what's, you know, when you glaciate, you're obviously cooling. And when you melt ice, you're obviously warming. It's how much we're adding to it. Again, that's the important part. If ice melts on Earth, if all of it melted, which, you know, I don't know if that could or could not happen, but certainly we would have problems even if all of it didn't melt. But if all of the Earth on ice melt, it would raise the water level. There's a map down below. You can see 230 feet, enough to flood all. We'd have to find someplace else to live. The nearest dry land would be up middle part of Georgia. Okay. So, and again, it doesn't have to melt all the ice. We're talking about Florida. What's the highest spot in Florida? 30, 40 feet, something like that. So the ocean level can rise significantly less, and we're still going to have problems. Okay, so back to this idea of the of water moving down the beach, right? Back to this idea of water moving out the rivers, being pushed down the beach, and beaches form, and all part of a natural process, and human beings get involved in this. If you live along the beach, you don't like the fact that your beach is getting eroded. You might not also like the fact that your beach is getting full of sand. You want it someplace in between. So you can build these structures, which we'll talk about, the ones that I have there in red. You can build these structures, and they're going to help you stabilize your beach. But unfortunately, it's really sort of a matter of robbing Peter to pay Paul. Every one of these structures, while it might fix what you have, actually makes it worse around you. So let's talk about those. Okay, growing fields. Groin field or a groin is just a bunch of junk. It could be old concrete, large boulders, whatever it is. And what they basically do is, you can see them along the beach. They build these vertical walls. There's the groin along the beach. A groin field would be a bunch of them, okay? All right, so that's great. If you're living here and your beach is being eroded, that's going to stop that. That'll help with you, okay? However, if your land is here and your neighbor builds a groin, what happens to your beach? Okay, so you build a groin. That starts replenishing your beach and screws the guy next to you. So you see, that's why you have to build groin fields. It's a reoccurring problem. You build one, you got to build the next, you got to build the next, because every time you do, you can even see the way the beaches are shaped in that picture, right? They're kind of shaped in that scallop. Every time you do, you increase the erosion downfield. So groin field, good or bad? No, not good at all, because all they are is a temporary solution. Now, jetties are like a groin field. The only difference is they're usually built in pairs. Jetties very often, many times, are inlets, right? Jetty Park. I think that's a picture of Jetty Park right there. And you can see even in that picture, isn't that Jetty Park? Where are my glasses? Yeah, I do. Well, it's somewhere. I don't remember where I took that from. There's erosion on one side, deposition on the other, right? So even though you've taken care of one problem, you've created another problem. So now you got to build another set of jetties or another groin, and you're going to build those down the beach, down the beach, down the beach, and it's never going to stop. See? But it's all because people are living along the beach. How about building a breakwater, right? You can build a breakwater with concrete, riprap. They can build with all, you've seen them, I'm sure. You can build a breakwater with anything that will stop the water. You run these parallel to the shoreline, and hopefully you protect the harbor. Well, unfortunately, the problem with that is you get the same thing you do like with the groins. You get deposition of sand here. That might be great for a while until you start choking out that area, and you start getting increased erosion downstream. Same problem. Right? Take a look here. Here's a picture. What's that? Santa Monica Pier? I've been to Santa Monica Pier. So they built themselves a pier, which is like a breakwater or a groin or anything like that at all. And notice how the sand builds up and is eroding on the other side. You can see that here too. It's eroding the beach on that side. And then this building up of the sand, this problem, how do you get rid of that? You got to dredge it, and that costs you money. So none of that's going to help. Oh, and this last one is the worst. Seawalls. Oh, that's the worst thing in the world that they ever put on a beach. For one thing, whoever thought that putting a concrete with steel rebar up against a beach where there's salt water was going to last? Doesn't take long for the water to seep between that concrete, start rusting out that steel rebar, and you're going to get those walls falling apart. It protects the coastline, protects the beach, but it ruins everything in front of it. Look at Daytona Beach. That's not what it's supposed to look like. It's one of the worst things you can put on the beach. It increases the erosion. One storm can remove the beach, just destroy it. Even the natural wave activity, because remember we talked about the sea oats? Sea oats keep the beach stabilized, so when a strong storm comes along and maybe this part gets eroded, this replenishes it. Okay, so storms can deposit sand. They can also help replenish sand. They can also be the cause that sand is dumped onto the beach face. But when you got a seawall, there's no dune. See, when they make a seawall, they get rid of the dune. That's like removing the heart of an organism. That's removing the heart of the beach. It destroys the beach. You continually have to pay money and dump sand in. And as far as I'm concerned, Daytona Beach is one of the ugliest beaches. I know people, oh, it's America's beach, but I find it disgusting. Alternatives. Well, you could stop people from living out there, but that's, yeah, it was. It took off like 70 foot of the pier, I think. It's amazing. Yeah, I can't stand Daytona. I think I went there once, maybe twice in all the years I've lived here. Stopping people from living on the beach is a problem, however, because they have the right to buy that land. Okay, so construction restrictions that limit building near the shoreline are going to be tricky at best. It's the best way to do it, the simplest way to do it, but in far the legality of it is going to be a problem. Originally, the National Flood Insurance Program, which you see down below, I've got some write-up from there, actually made it worse. The reason why that is the National Flood Insurance Program would actually provide subsidies for insurance policies for people living on the beach. And if you look right there in the red, Florida was the top state that was receiving what are those numbers? Is that $299,000, whatever? I can't see what the numbers, but 268,000 policies, which again is subsidized flood insurance for people living on things like barrier islands. So the federal government, you and I, for example, through taxes, would pay these people who live on the beach money so they could, or help pay some of the money to help replenish their beach, like hire that guy in the payloader there to push more sand up on their beach. That's $5 to $10 a square yard. A dump truck holds 60 square yards. Think about how much sand you got to replace. So these people living out on the beach are getting your tax money to replenish the beach, and they're the one that are making it the way it is. Now, I understand living on the beach is good. However, now that has been changed. Recent changes in the FEMA and the Federal Emergency Management Agency, they have regulations to start curbing that. So if you live out on the beach, as far as I'm concerned, you probably got the money to afford to replenish the beach yourself. Unfortunately, you're the one living the way they do. It's causing the beach. And beach erosion is part of the natural process anyway. You know, where do you get the sand? Well, you can get the sand offshore. Bring the sand from offshore, and then you just make it worse, because then you make offshore worse. Oh, this is the Indian River Lagoon. These are spoil islands. They dredge the lagoon to keep it deep enough, and they dump the dirt, and these are spoil islands, the stuff they take out of the... Partially enclosed, it's caused by a barrier island. It's open, of course. You all know about the inlets. A lot of variability. It's kind of like those organisms that live in the high and the low tide zone. A lot of variability here. A lot of variability in temperature, a lot of variability in salinity. It's going to be much more salty near the ocean, a lot less salty, upstream. The pH turbidity, which is murkiness, how murky the water is, that's going to be different depending on how much rain there is. The depth is going to change. So organisms that live in the estuary are going to be an awful lot like critters that live in those tidal zones, right? They're really going to be taxed environmentally or evolutionarily to be able to deal with these variable habitats. It's one thing to live in one place that doesn't change. It's another thing to live in a place that constantly changes. Now, where do they come from? Well, sea level rise, as I told you, right? About 18,000 years ago, after the glaciers began to retreat, the sea levels began to rise, and you could end up having them in a variety of ways. You could flood a river valley, like along a coastal plain. A fjord could occur, like in Norway. You could get that's an estuary, and that's the glacier going to be retreating. The bar-built ones, the barrier islands that we talked about, a bar-built or a barrier islands, the same thing. There's San Francisco. Isn't that San Francisco? Yeah. California's San Francisco Bay. It fell, so the water rushes in. And of course, on the left is a picture. I'm reminding you that that's what we have. We have a barrier island. All those estuaries, that's how estuaries can form. So they can basically form where a river valley gets flooded, and sometimes that happens because of erosion occurs and lets part of the ocean in, like another inlet forms along a barrier island. And again, with the glaciers, barrier islands, as well as land drops. That'll cause an estuary. Now, estuaries are like those little ponds that are inlet at the beach, right? And they're always nice and warm compared to the rest of the water, but you can imagine living in there. Living there is going to be a problem. So estuaries, like I said, are very habitat rich. There's a lot of things going on. Like, for example, there's the mixing of the waters, the mixing of the salt water. For example, there's the vertical mixing, right? This is what occurs in a shallow, low volume. The net flow is from the head to the mouth. This is the kind of mixing that you're going to get, is the vertical mixing. Now look up at the top, right? So the mouth is where it opens to the ocean. So the numbers are the salinity. So you notice that the salinity is going to be higher near the mouth, lowest near the head. And this is vertically mixed. It's kind of a very sort of simple pattern. When it starts getting stratified at about a moderate depth, the salinity is going to increase, but you're going to get these layers. You're going to get this mixing that occurs. So the lower salinity water, because it's less dense, is going to move out, and the higher salinity water is going to move in. See, remember, salinity and density are related. So the lighter salinity water at the top is going to go this way. And that's going to cause, it's like the Ekman transport, remember? It's going to cause water molecules to rub against each other, and through a conveyor belt kind of process, that's going to bring salinity down, deeper or heavier salinity water down deeper. So you can be slightly stratified, you can be really highly stratified, and highly stratified you can have a much deeper, it's all about depth. So the deeper the estuary is, the more stratified you're going to be. You have a highly stratified estuary, and this actually produces haloclines, or areas in which remember, halocline is like a thermocline. It's the area where the salinity changes very quickly. Other areas can actually, like in the mouth of deep, very high volume rivers, the river water can go way out past the end. The Amazon River, for example, the freshwater part of it, you can find fresh water from the Amazon River 100 miles out to sea. That's how much water is flowing down. But what that can do, actually, if you look down below, you can see that a wedge of salt water, this is also in the last picture, what we call a salt wedge can move in under the river water. All right, so this river water flowing out to sea is causing this spinning thing like we see in the slightly stratified. So this salt water can actually move in, and organisms that don't normally find themselves in such salty conditions can be affected by that. And of course, that's the problem with the tide, right? This crab guy, he's got to deal with a lot more of that saltwater wedge problem when it's high tide than low tide. Now, like I said, estuaries present their challenges, but one of the nice things that they do provide is a lot of times they provide a really good nursery. Okay, like for example with Atlantic menhaden, you see over on the left, Atlantic menhaden spawn in the estuaries, they're larvae, and they remain there till they're about a year old. And then they come back, and the larvae of the eggs are laid just offshore and drift in with the incoming tide. Now, the reason why the larvae are brought in there is because of the fact that it's safer in there, right? It's shallower water, less predators. Tarpon do the same thing. Tarpon's young spend their time in the estuaries. The problem with that, since it's good breeding grounds, though, is sometimes its proximity to shore, and the fact that it's basically a drainage canal. Look at the picture there of the Chesapeake Bay. Is oftentimes these areas become problematic because of all the stuff that drains into them. And many times what happens is areas, because of all the pollution, it'll actually remove the oxygen from the water before it to become anoxic. That's what the purple part is. It becomes anoxic without oxygen. And even though fish live in water, they still need oxygen. So we got to be careful with that, right? As human beings, living close to estuaries and letting all that stuff wash out the estuary. And then related to estuaries are lagoons, right? This has a bit of a more restricted circulation. It's kind of like the Indian River Lagoon. Like I have that nice little sticker in the upper right. I love that Indian River Lagoon. A lot of changes. A lot of changes in salinity. A lot of changes where you are in the lagoon. Closer to the mouth, the higher the salinity, the higher the tide effects. And it's going to change with the dry and the rainy season too. Salinity doesn't get affected that much in the ocean or that quick or that concentration with the rain out in the ocean, but definitely a problem in lagoons because of that restricted water flow again. And many times you'll get like a freshwater area, well, oftentimes, and then the salinity will vary as you move down the lagoon. You'll have transitional areas, which the water is called brackish. You can actually get hypersaline areas that are very salty, depending on the evaporation rate, how much water is flowing in. If it's a heavy storm, a lot more ocean water flows in. This area is going to become a lot saltier, right? And remember, the big thing about all this with the lagoons is that balance between the fact that they are very delicate ecosystems with organisms that have very delicate balance that they got to deal with. And yet they're very close to human beings. So there's a very distinct possibility of us damaging if we're not careful, okay? That's kind of what the big thing we take away from all that. Wetlands are similar. Wetlands are important because they're good as like nature's kidney, basically. They filter out pollutants. They filter out fertilizers and nitrates. Wetlands are formed because many times what happens, like we have here in Florida, down in the Keys, the water table is close to the surface, so you get a lot of water at the surface. Very productive, very diverse ecosystems. This is the prop roots of the red mangrove. Tons of little fish live in here. It's kind of like the estuaries in a small scale. I always tell folks, if you're ever snorkeling down the Keys, gather up your muster and snorkel up as far up into these prop roots of those red mangroves as you can. You'll see all sorts of little fish, like a little nursery in there. Wetlands overall, not just the ones in the Keys, produce about half of the commercially or the nursery for half of the commercially important fish in the United States. So you can see that's a very good reason to protect them. They soak up the nutrients, like I said. They do a little bit like the barrier islands by dissipating the wave energy, right? So they're good for that. They act as kind of a retention pond too, because the water that flows into the wetlands keeps it from flowing on to the drier land, right, and affecting our land, if you will, or where we live. Once again, though, the problem is they're coastal wetlands, right? So they're along the coast. And anything that happens along the coast can affect the wetlands. That's what I'll talk about in the last slide. Mangroves is what we have in the tropics. That's what we have. Very salt-tolerant mangrove trees. Thick cuticle leaves, which keeps them from drying out. These are mangrove pencils. These are the seeds of mangroves. Mangrove seeds, when they're dispersed, when they fall off, they're just about ready to grow. What they do is they float around in the water. You might have seen them at the beach, actually. They float around the water vertically until they find some dirt, and then if they can take hold, their roots, they're ready to go right away. They're what we call basically a live bearing seed. It's almost like a young animal in a way, because it grows right away. And they have those prop roots again that help prop them up and to provide all those great nurseries. Prop roots allow them also to kind of help them regulate the amount of salt that they absorb. It's salt marshes when you go higher or lower than that. Salt marshes up above, there's a salt marsh in Morro Bay, California. And these can be mostly populated with grasses, more grasses than brushes like mangroves. Halophytic grasses, things that can deal with salt. The reason why it's much more important out in the salt marshes for these guys to be able to tolerate salt, even more so than the mangroves, is how often the water level drops in these salt marshes and the water evaporates. And water evaporates, it doesn't bring the salt with it. Right? Salt stays behind. And as I said, about half of the U.S. wetlands have vanished. We have a real problem with that in Florida. It used to be a law that a developer had to recreate 2 acres of wetland for every one he destroyed. I don't know if that's a law anymore, but we found out, unfortunately, that creating a wetland is like, it's not as easy as it sounds. So a lot of these created wetlands weren't doing their job. And a wetland, again, is a filter. It helps filter out nutrients. It absorbs excess water. Unfortunately, people living along wetlands, we've done things to try to protect it. There's the Office of Wetlands Protection in '86, which really helped drop the destruction, made it a lot more difficult for developers. Well, developer, what he does with a wetland first is he drains it. The Altamont Mall here in Orlando, the Altamont Mall always had problems, may still have problems with flooding, because the Altamont Mall was a wetlands. It was a drained and filled in wetlands. So they were miffed when the thing kept flooding. Well, that's because that's the way the land is set, and that's where the water wants to go. You know that the triangles on the right-hand side, more than half of the wetlands, right? 287 million hectares. A hectare is about 2.5 acres. So 2.5 million acres down to something like 106. And if the sea level rises, we estimate to lose another 60%. Not good. Wetlands are very important, as I said, for nurseries, pollution filtration, ecosystem stability, anthropogenic, the word in the red. Learn that word. It's a good word to remember. That means human caused. Like global climate change. Right? The anthropogenic factors of global climate change are the parts I was saying that makes it worse, right? And of course, another thing, we dump all our garbage in these wetlands areas too for living there, and that's not good. So it's obviously something in Florida. This is much more important than maybe other parts of the country because of the fact that Florida has so many of the wetlands. All right, I'm going to stop the recording.